Hello and welcome to Carlum Cymru e-sgol sessions. My name is Mr. Ridd and today we'll be looking at WJEC Physics Thermal Energy Transfer. So let's get into it. Now, I have to start off with, as always, a list of learning names that we hope to cover in this presentation. Feel free to pause the video at any time and review these learning names. Perhaps you might want to check them off as you go. That's entirely up to you. Right, so first of all then, we need to know that temperature differences cause heat energy to be transferred by conduction, convection and radiation. This top first learning name. So to understand what we mean by the direction of heat transfer, I have put a few examples up on the screen here for us to think about, okay? Now, when you think of a hot cup of coffee, like we've got here, the coffee itself is hotter than the surroundings. And as you're aware, over time, a hot cup of coffee will cool down. So that heat energy has gone from the hot cup of coffee into warming the air around it. So in this instance, we can think of the heat traveling from hot to cold. And in fact, that applies to all of these examples. So when we say the direction of heat transfer, we don't mean left or right or up or down. What we really mean is it's always from hot regions to cooler regions. Think about this metal poker now onto this fire here. Heat energy is going to travel up the rod towards the person's hand. It's going to go along that metal rod, it's going to conduct along that metal rod from a hotter region, i.e. in the fire, to the cooler region next to the person's hand. If I have a bath, and you'll all have experienced this, I'm sure, you put hot water in your bath, maybe to top it up, to add a little bit more hot, and what happens is the hot kind of stays down this side of the bath. But eventually, of course, that hot water, that heat energy will spread from the hotter end of the bath to the colder end of the bath. And normally, of course, we speed this process up by giving it a bit of a zhuzh. These other examples are the same principle, but they work in the opposite direction. So let's imagine now I put a can into the fridge. Just imagine I'm putting this can into the fridge to cool it down. What will happen then? Well, if you think about it, the can is warmer than the fridge itself, isn't it? The can is warmer than the fridge. If we just bought the can from the shop and we want to cool it down because it's a hot day and we want a cold drink, then we're going to put the warmer can in the colder fridge. And in this situation then, of course, the heat energy is once again leaving the can, okay? And the can is getting colder. Now, it's very important that we remember and acknowledge that it is not the case that it's in some way, the can is in some way taking on cold, which is often how it's interpreted. What's actually happening is the little bit of heat that's in the can is leaving the can and warming the surroundings of the fridge. And in doing so, when that heat energy leaves the can itself becomes cooler. And then if we think about a hot sunny day, we've got an ice cream here, what's happening? Well, we know that the ice cream is colder than the surroundings in this situation. So the heat energy here now is actually going into the ice cream, causing it to melt. All right. So direction of heat transfer always from hot to cold. Okay, let's move on. The reason I ask this next question is because to understand thermal energy transfer on a deeper level, a level which is suitable for GCSE studies, we have to understand the nature of matter. We have to understand or recall solids, liquids and gases. And in particular as well, we need to understand this idea of well, I don't want to spoil it just a second. Let's just have a look at this riddle and you'll understand why I'm talking about it in a moment, I'm sure. So what is heavier, a ton of feathers or a ton of bricks? You might have heard this riddle before. And a lot of people obviously incorrectly answer, well, it's a ton of bricks, and that's not the case. They both weigh a ton. Now, How would a ton of feathers and a ton of bricks look different to each other? Well, obviously one's feathers, one's bricks, but a ton of bricks would occupy quite a small space, all right? It would be less than a meter cubed, whereas a ton of feathers would probably fill most rooms. So you can have a ton of any substance, but the thing that determines how much volume it occupies is a concept known as density. And density is important when we think about thermal energy transfer. So it tends to be the case that substances that are quite dense, substances where particles are really close together, tend to be better conductors of heat and transfer heat more effectively. Whereas other things which have a lot of air in them, like feathers, all right, or maybe a duvet or foam, these tend to be very low density and they tend to be very poor conductors of heat, all right. You can think about the problem in this situation as well. Here we're keeping the volume constant. So a bowling ball and a football are roughly the same size. But of course they've got very different masses, they've got very different weights. The reason why, well, as you know, a football is filled with air and a bowling ball is a solid object. It's pretty much just, I don't know what they use, like a epoxy resin or something like that, all the way through. And again, here the difference is density. So we've got a lot more particles, a lot more matter, a lot more stuff in the same volume when it comes to the bowling ball in comparison to the football. So again, what's similar, what's different? Well, the volume, you could say, is the same, all right? But the mass of the two objects is different. And that is what gives these objects different densities. So how do we work density out? Oh, well, let's have a look at this definition first. I'm going to have to hide myself here. Okay. So density is the amount of stuff in a certain amount of space. That would be one definition, a simple definition, but a better, more scientific GCSE style definition would be density is the amount of mass in a certain volume. Okay, that's a better definition. We prefer that one. Okay. Here we can think about the definitions of density, mass and volume then, and if you want to pause the video and have a go at this yourself, then feel free to do so, but I'll just jump ahead and do it. So density then is the amount of mass per unit volume or unit of volume, amount of mass in a given space. Mass then is the amount of matter or stuff that an object contains. Yeah, matter is just a scientific word we use for stuff, so don't get too hung up on that. And then finally, volume, the amount of space that an object occupies. Then we can think about the units of measurement. So the unit of measurement for mass is the gram, or it could be kilograms. The unit of mass, the unit of measurement for density, well, let's do volume first, is centimeters cubed. Have I done this right? Yeah. So the volume, oh no, hang on, Mr. Riz, what have you done? Uh-oh, let's find a rubber here somewhere. Is there? I've got a tool. Oh dear. I'm going to have to. Can I rub this out? Oh no. Okay, so mass is measured in grams or kilograms. So volume, this one here is measured in centimeters cubed. And then finally then density is grams per centimeter cubed. It could be kilograms per meter cubed. This could be meters cubed. So depending on what you're measuring will determine maybe the unit of measurement that you use. If you're measuring small things, you might be using grams and centimeters cubed. If you're measuring larger objects, you might be using kilograms and meters cubed. Okay, so calculating density. Density is equal to mass divided by volume. And just like I said there, it can measure in either of those units, either kilograms per meter cubed or grams per centimeter cubed. Just be really careful, look at the question, what are the values of the quantities measured in, use those to guide you as to what unit of measurement you use for density. Now, let's put this into a formula triangle. There is another video available on the website, which is all about the mathematics that supports physics. So if you're really confused about how you use things like formula triangles, units of measurement, standard form, all those things, then please go check that video out, and hopefully it'll make all this a lot easier. So I'm going to skip ahead, assuming that you know how to use a formula triangle, and we're going to put these quantities in right now. So we'll put the M on the top for mass, because we know we need mass divided by volume, and then we're going to put D just here, put a little multiplication sign in, and that allows us then to calculate our different formulas. So if I need a formula for mass, we cover up the M is equal to D times V, and then from a formula for volume is equal to mass divided by density. So those are our three formulas that we can get from this triangle. Let's have a little look at calculating volume then, and you'll have done this in maths, I'm sure. So if I need to calculate the volume of an object, and I got three dimensions, as in the case of a cuboid, then it's simply a case of multiplying the length times the width times the height, which in this case would be 10 times 4 times 4, 160 centimeters cubed. Another example here then, different cuboid, but again, same principle, length times breadth times height, or width, as it was in the previous one, doesn't really matter. 30 times 12 times 5, 1,800 centimeters cubed. Okay, so calculating density recap then, if we wanted to work out the density of an object, let's say it had a mass, we measured the mass on a balance, and we measured the mass to be 64 grams, and we knew its dimensions, and we knew it had a volume of 32 grams, and then we could just simply do density is mass 64 over 32, giving us 2 grams per centimeter cubed. How do we know it's grams per centimeter cubed? Well, the question gives us the mass in grams, and we've worked out the volume in centimeters cubed, so I know it's going to be grams per centimeter cubed. And what that basically means, if you have 2 cubic centimeters, if you have a cubic centimeter of this material, whatever it might be, then it would weigh 2 grams. To give you some perspective, water is equal to 1,000 kilograms per meter cubed. Sometimes it's worth thinking about what that means, because it gives you a feeling for what density really is. What it means is, if I had a cubic meter of water, which I'm sure you can imagine, think of a cube which is 1 meter wide, 1 meter tall, 1 meter deep, then that cube of water would weigh 1,000 kilograms, or what we call a metric ton. Right, so that's fine for measuring the density or calculating the density of a regular shaped object. Things like cuboids, very straightforward. You won't be asked, I've never seen it asked, that you're asked to determine the density of something like a cylinder. But in theory, they could give you the formula for calculating the volume of a cylinder, but it's highly unlikely. What if, though, we needed to calculate the volume of an irregularly shaped object, like a rock or a crown or a person? That's harder, because you can't do the length times breadth times height thing, because the dimensions of those objects are all strange, and they're irregular solids. And the reason I put this slide up when I'm teaching is to just think back to the person who discovered the method for determining volume of an irregular solid. And that chap famously had like a light bulb moment, and he famously screamed, "Eureka!" And this guy was Archimedes. And as the story goes, Archimedes had this issue where he needed to determine the mass the volume of a crown to work out its density, to decide whether a crown was made of real gold or fake gold, because they knew the density of gold. And the King of Sicily commissioned him to solve this problem. And famously, he got into a very full bath. And when he got into the bath, the water poured out over the sides. What he realized was that the amount of water that poured out was equal to the volume of his own body. And as long as he could collect that water up and measure that water, then the amount of water he measured would be equal in volume to the volume of his own irregularly shaped body, which was the eureka moment. And that's still, in a sense, how we measure the volume of an irregular solid today. Now, you might have done this in school, you might have done this in your lab, okay? You should have. If you haven't, well, it's not good enough, is it? Anyway, you can take an irregular solid like a rock or something like that. All right. You pop it into a cylinder, a measuring cylinder with water in it. You record the water level before, you record the water level after, and of course the difference is the volume of the rock. So there's a change in volume, and that change in volume is equal to the volume of the rock. So that's how we work out the volume of an irregular solid, and then of course we can quite simply use our density equation as before, as long as we know the mass of the rock. So let's have a look at what we've done. We have so far completed the idea that thermal energy transfer or heat energy transfer is caused by temperature differences. Now, we haven't gone into the details of conduction, convection, and radiation just yet, but we have covered the idea that it travels from hot to cold. And we've also covered this idea of density as well, the mass, divided by volume. Next, we're going to talk about the differences in the density between the three states of matter and the arrangement of the atoms and molecules. Now, I'm sure you've probably seen this, most likely at Key Stage 3. I'm not going to discuss this in any great length, and again, like before, if you want to pause the video and maybe make some notes and have a good read of this, then feel free to do so. But in some ways we can think of this as prior knowledge. So in a solid, the particles are really densely closely packed together. In a liquid, they're very close, they're still sort of touching, but they're free to move around. And in a gas, they are spread out. There's large distances between the particles, and they're able to zip around and move. And those are the important bits, really, that we need here. The fact that you can compress a gas is not so relevant in this particular field of study when we're thinking about thermal energy transfer. So here is a nice little diagram showing all three different forms of thermal energy transfer, and heat can travel around in one of three different ways: by conduction, by convection, and by radiation. So let's start off with looking at conduction. So conduction, first of all, happens in solids. Does it happen in liquids and gases? Well, yes, but to such a small extent that it's really quite negligible. All right. Conduction is really a phenomena that happens in solids, and it's down to the arrangement of the particles. And again, back to that word density. It's the density of solids that give them this ability to conduct heat. So if I heat a metal bar, for example, or a solid at one end, okay, then what happens is these particles gain energy. And when these particles gain energy, they begin to vibrate, which means they wiggle about in the sort of structure that they're in the lattice between the bonds that they have, and they will wobble and vibrate back and forth. In fact, when you touch something that's really hot, like a frying pan or something like that, okay, then what's actually happening is that the sensation, you're detecting the vibration, the rapid vibration of the particles, and that's transferring heat to your hand really, really quickly and causing a burn. Anyway, the point is that if you heat this metal bar at one end, the thermal energy will go from the hot end to the cold end. And what we need to understand now is the process by which that happens. And essentially the particles vibrate more when they're heated. Because they are vibrating, they collide and bump into the neighbouring particles, the ones next to them. So for example, this particle will start vibrating because other particles will bump into him, and then he'll pass his vibrations on to this guy, and then this guy will pass the vibrations on and on. So they vibrate, they collide, and they pass the energy along the solid until we end up with the heat energy transferring from the hot end to the cold end. And that is essentially it for solids as a general category. And that explains how heat will get from one end to the other. It's a bit like if you're in the dinner queue, maybe you can relate to this. You're in a dinner queue and someone pushes from the back, and that energy kind of passes through the queue as everyone collides with each other as it goes from the back to the front. A bit like a domino effect, you could say. Now, it is also true, though, that certain materials are better conductors than others. And the category of materials which are by far the best conductors are solids. Are metals. Now, why is it that a metal, such as copper, is such a better conductor than something like wood or glass? Because they don't conduct heat very well at all. They are solids, wood and glass are solids, but they don't conduct heat very effectively. Well, it's all to do with the fact that metals have a lot of what we call free electrons. Okay. Now, free electrons are the same particles that make metals such good conductors of electricity. It's these free electrons that create an electrical current through a metal, which is obviously how we have electricity and how we transfer electricity. But it's that same particle, the electron, that is also responsible for transferring heat in metals so much more effectively than in non-metals. Because just like with electricity, a particle can whiz all the way through a metal from one end to the other, make a collision with an ion, one of the atoms, and pass the energy on. And this process happens then in addition to that vibration that we talked about in the last slide. So you've got two things going on. You've got the particles or the atoms, the metallic atoms, vibrating and bumping into each other and passing the energy on that way. But in addition to that, you've got the electrons which are whizzing along and passing the energy through the material. So that's why they're such better conductors. I'm going to leave this up here. If you were asked to explain why metals are such good conductors of heat, then this would be a nice answer. It could be a part of a 6-mark question, for example. And I've used all of the keywords like vibrate, atoms, collide, metal, transfer energy, heat, okay? Lots of really important words here. Again, pause the video, write it down, or just give it a read. That's entirely up to you. Right, here's a little question then. So if you're barefoot, not barefoot, good one, monkey, and you walk from a rug onto a tile floor, which is colder. Why does it feel colder? What's going on? We've all noticed this, isn't it? Maybe you've walked into the kitchen and you've gone from carpet to tiles, and instantly you go, oh, the kitchen floor is cold. But isn't that strange when you think about it? Because your house is probably the same temperature everywhere. It's not the case that your kitchen is kept in some kind of Arctic condition, that the rest of the house is 20 degrees, yet the kitchen is at a really chilly 5 degrees. That wouldn't make any sense. There's no barrier, is there? No, in fact, your whole house, more than likely anyway, I mean, I don't know where you live, but your whole house is more than likely to be the same temperature, say 20 degrees. So why is it then that the floor feels colder? Well, as really good scientists now, we should be able to answer this question a little bit more effectively, because it's all to do with the transfer of heat energy. The point is that when you're walking on the carpet, carpet is such a poor conductor of heat. It's made of a non-metal, it's very low density carpet is, got lots of air sort of trapped inside it, it's such a poor conductor that the heat doesn't leave your foot. I'll draw a foot, look. Oh, here we go. Oh, do you know, that's not bad. That's not bad. Come on. Yeah, so if you're on carpet, the heat doesn't leave your foot very effectively. However, as soon as you step onto that tiled floor, the tiles are harder, they're denser, they're made of a more thermally conductive material. And what that means is that the heat in your foot, okay, your nice warm foot, leaves your foot and gets into those tiles really quickly. The thermal energy transfer is faster. So it's not that the cold is getting into your foot, as some people seem to perceive it. It isn't that. It's that the heat is getting out of your foot, making your foot colder. So yeah, that's how that works. Just in case you ever wondered why some stuff feels colder than others, it's more than likely the case that it's just a better conductor of heat and it's transferring heat away from your body. Anyway, here's just some stats about conduction. We all love a good table. Who doesn't? And you can see there that some materials are really poor conductors, like air, 0.026 watts per millikelvin. Don't worry about the unit of measurement, just realize that 0.026 is really low. But something like copper and silver, even more so, are very good conductors. You'll notice the diamond is very, very high. Right, so we've done this guy. Difference in the three states of matter, yes, in terms of the arrangement of atoms or molecules. Now we're on to describe how heat energy is transferred through solids by considering the motion of particles. Done that. Describe how heat energy is transferred through metals more effectively than non-metals. Done that. We're cooking on gas here. And then describe convection currents in liquids and gases in terms of particle motion, volume, and density. Right. So that's solids. So when you see a solid object in an exam and it says, how did the heat energy pass through the wall, for example, then you go, okay, walls are solid. Yes, walls are solid, so it must be conduction. Job done. However, it is also the case that heat energy can be transferred through liquids and gases. And we're going to get on to now looking at that process and in particular understanding convection. Here are a couple of examples of convection in action. A hot air balloon and a lava lamp. I don't know if you know what a lava lamp is. They're kind of cool back in the 90s and the 70s. They'll probably do a comeback again. You know what these things are like. Anyway, how do these things work? Well, you know that in a hot air balloon, maybe you don't know. I don't know. Maybe you do, maybe you don't. But there is a burner there that burns gas to create a lot of hot air. And you know that that hot air will rise. And in fact, it makes the whole balloon fill with hot air, and hot air rises. And that's a very basic idea behind this concept of convection. We're going to look at it in a bit more detail now. But when we heat a liquid or a gas, it will rise. Another example then is in the lava lamp. If you heat up the wax, then as the wax gets hotter, it becomes less dense than the water around it, and it rises through the liquid. Now, it's also true as well, the opposite process. So when these things cool down, when the gas cools down, it will sink and fall. So if you want to come down after you've had your lovely hot air balloon ride, then all you've got to make sure you do is stop burning gas. Maybe you run out. That'd be scary, wouldn't it? I've never really fancied a hot air balloon ride, largely because you just don't know where you're going to end up, do you? It seems a little bit like, I don't know, I'd like a propeller or something. It seems a bit, a basket. Anyway. Yeah, this is an odd one as well. This can help thinking about convection, because convection and hot air rising is all to do with that concept of density again. You can try this experiment yourself. if you get some Diet Coke and some regular Coke, or full fat Coke as we call it in our house, then if you pop them in a jug of water or some kind of container, what you'll notice is that one sinks and the other floats. And why is that? Well, one is denser than the other. Can you think which one is denser? The one that sinks to the bottom. So this is denser than the Diet Coke. And what that means is that the sugary liquid, the sugary Coke then, if you like, is heavier than water, or if you like, denser than the water around it. Because it's denser than the water around it, it causes it to sink. Whereas the Diet Coke will be less dense than the water around it and cause it to rise. I don't know if I've done any kind of copyright infringement here, so I'll just finish by saying the colas are available. Oh, that's funny. I was wanted to say that. Anyway, explain why hot air balloon rises then. So we've got to get right now into the nuts and bolts of physics, and for your potentially really hard question where you've got to give some kind of 6-mark answer or a long description, we're going to need to talk about particles, okay? So when we heat the air, what's really important to remember is that the air particles start moving a lot faster. If you remember when we looked at our particle model for a gas, okay, we've essentially got just a few gas particles whizzing about. But when we heat up a gas, we give them loads and loads of energy to whiz off. And they start moving faster. The effect that this has is to cause the gas to expand. And when the gas, or the liquid for that matter, expands, crucially it becomes less dense. Think back to what we discussed when we talked about the concept of density. Density is about how much matter, how much stuff you have in a given volume. So if I have the same amount of stuff, liquid or gas, I heat it up and they start moving faster and the whole thing expands, or the volume increases. If the volume of that liquid or gas increases, but the amount of that liquid or gas, i.e. the number of particles, remains the same, then that's going to have an effect of reducing the density. The density is going to go down because, if you remember, density is mass divided by volume. So if the volume gets larger, if the term on the bottom then, if this one gets larger, if it increases, then that's going to have the effect of reducing the density. And the knock-on effect of that will be that that object that has a lower density, or if you like, the air inside the balloon now, has a lower density than the air outside the balloon. The air outside the balloon's got a higher density, and therefore that lower density air then is going to want to float, or it's going to want to rise, and that's what causes the hot air balloon to rise up into the sky. So there's a lot there, isn't it? We've got the word expand, we've got volume, we've got particles, we've got speed, we've got density, all right, and that's why I put it all into a nice answer for you. And again, just like before, please pause the video, give it a read. Panicking now because I've written these things and I haven't really checked for spelling, punctuation, and grammar, but you get the gist, and I do apologize for any mistakes. I don't think there are, but okay. I can see it right now. Oh my God, particles gain energy and move faster. This is because the gas. This causes the gas to expand and become less dense. Yeah, so it's all there. I put the keywords at the bottom for you as well, just in case you wanted to refer back to those to write your own answer. So that's convection. It's important as well to mention that convection happens in liquids and gases, not in solids, because of course the particles are not free to move around. That's an important part of this. Right, on to the last method of thermal energy transfer. This one's quite different to the other two, because the other two involve particles. But how does heat travel through space? Because I don't know what you know about space, but space contains no particles, no matter. It's not technically true. It's got a very small amount of matter in it, but for the most part, you can think of it as being a vacuum, completely empty. With that being said then, how is it that the sun transfers its energy through space from, that distance, 150 million kilometers away? It's tricky, isn't it? Well, if there are any particles to do it, it must be because it's traveling via the sun's light. And in fact, as you'll come to see when you study waves, when you look at the electromagnetic spectrum, there's a part of the electromagnetic spectrum, a part of light, which is all to do with heat transfer, and that's the infrared part of the spectrum. So it's the infrared light from the sun that transfers heat to the earth across the empty vacuum of space, where you cannot have any conduction, you cannot have any convection, because there are no particles present, and heat cannot travel by that method. All right. It's a nice little experiment, which I used to do actually, but my infrared detector broke, and then someone stole the new one I bought, and I haven't replaced it. Isn't that sad? But this is a famous experiment known as Leslie's cube. It's a simple little setup. You pour some boiling water into the cube, and then you use your infrared detector to look at which of the surfaces are emitting the most infrared radiation. And you can obviously position or rotate the cube, and what you find is that the matte black, which is on the other side, which we can't see, the matte black side of the cube, it emits the most infrared radiation. So infrared radiation and the amount of infrared radiation that's emitted is dependent on the color of the surface from which it is being emitted. Also, it is true that the amount of infrared radiation absorbed by a surface depends on its color as well. And it's also true that matte black surfaces are the best absorbers and the best emitters of infrared radiation. And you'll know this anecdotally anyway. If you've ever gone out on a hot sunny day and made the mistake of perhaps wearing a dark coloured t-shirt, then you'll know that people say it attracts the sun, don't they? They say that all black attracts the sun. I need you to correct these people, because you're scientists now. You need to say, no. Black, matte surfaces are better absorbers of infrared radiation. Put them straight. Put them straight. Yes. So, you see this utilized. The worst then, or the poorest transfer waves of transferring infrared radiation are with shiny, lighter surfaces. All right. So something like foil. One of the reasons why foil is so effective at keeping things warm after they come out of the oven is because when you put that foil over it, it is going to reflect the infrared radiation being, given off by whatever food you brought out of the oven. Say it's a chicken. The chicken's emitting infrared radiation because it's hot, and you put foil over it, and that will reflect. It will reflect, which is the opposite of absorb, infrared radiation back in. So, I think we've described convection in liquids and gases in terms of particle motion, volume and density. We've done radiation as well, which is up here. And then finally now, we want to look at how this kind of applies to heat losses around the home. So let's have a little look at that. Little image for us to think about. What's the science in this? We've got two houses which are, very, very similar looking. If you were playing Spot the Difference, though, you'd notice that the house on the left, you can see, hasn't got as much snow on the roof as the house on the right. Why do you think that is? I'm sure you're screaming at the screen with your answers now. But I can't hear you, so I'm just going to answer it for you. It's all to do with the fact that one of these houses is better insulated. It prevents heat from escaping better than the other. And which do you think that is? If you thought that the house was better insulated was house A, then you were wrong. The house with the better insulation is house B. The reason we know this is because house B hasn't transferred as much heat through the roof. It hasn't let as much heat escape, and the evidence for that is the amount of snow. Whereas house A has allowed a lot of heat to escape, and as such, it has melted a lot of the snow. So there are ways in which we can reduce the amount of heat loss from our homes, which is important for a number of reasons. First of all, it's nice to be toasty and warm. Who doesn't like being toasty and warm? As you know, we like to chuck the heating on whenever we get the chance in my house. That's for certain. Probably a bit too much if I'm perfectly honest, more than I'd like anyway. But it also saves on our bills. So if our house is well insulated and we're not losing as much heat energy because when we've got drafts, so the heat's not escaping, then we don't have to spend as much money running the boiler and having the central heating on. So that's a good thing. And then lastly, if we're using less heating, we're burning less fossil fuels. So our boiler and the boiler in your own home is most likely burning gas to heat your home. If we're burning less gas, then we are creating less CO2. We've got a smaller carbon footprint, which is another term that's going to come up, and that is going to hopefully have some kind of impact on reducing global warming and climate change. Although it is a small amount. It's the idea that if everyone does a little bit, it'll all add up. So here are some images. Loft insulation. So people will install very, very thick loft insulation, which is this, like, you might have seen this like fiberglassy, kind of wiry, nasty stuff. You'll notice the person working with the loft insulation is wearing a mask, which is absolutely necessary because any of these little fibers can get into your lungs and cause all kinds of damage. Don't mess with that stuff, okay? Not good stuff, but excellent once it's in the attic, of course, preventing the heat energy from escaping. Now, the means by which this happens, well, if you think about it, in the rest of your home, as you heat your house, all the warm air is going to rise through the house by convection. So we think about it, if I'm talking about warm air, okay, that's going to be convection because convection happens in liquids and gases. So the heat energy then is going to rise, it's going to go up through the loft, out through the roof, and you're going to lose it. If you've got very thick insulation, then this basically creates a little bit of a barrier, stopping that thermal energy from leaving, keeping your house warm. This is double glazing over here. So double glazing prevents thermal energy transfer as well, quite effectively, by having an air space between two panes of glass. That's why it's called double glazing, because it's made up of two panes of glass. And if you're interested to do so, you could go and have a look, because your house is more than likely to get double glazing, and you can prove for yourself that in fact your windows are made of two panes of glass. Some of you might even have triple glazing if you're well posh. Triple glazing is, well, exactly what it says in the tin. So you'll have two air spaces. And the air space, if you remember, we said about air being such a poor conductor of heat. Air is such a terrible conductor of heat because remember, the particles are so far apart, and if one air particle vibrates, it's not likely to bump into the other one. So heat energy is not effectively transferred by conduction. It's not effectively transferred by convection because this little pocket of air is trapped, okay, between the two panes of glass. And in fact, in reality, they don't even have an airspace. It's a vacuum. They suck the air out from in between the two panes of glass. So there can be no convection, no conduction, and the only way heat energy can pass through them is by radiation. So they become very thermally efficient. It means that not very much heat is transferred through your windows if you have double glazing, for the reasons I just mentioned, okay? Draft excluders are another means by which you can prevent heat losses from a very cost-effective means. All these things have a certain cost associated with them, and not in this topic, but one of the things you have to consider basically in your year 10 course is something called payback time. And payback time, oh, do you know what? I'm going to put it in here actually. It's so relevant. So payback time is the cost divided by the savings per year. So if my loft insulation here, imagine it cost me £80 to install. So that would be my cost. My cost would be £80 to install. And let's imagine it saved me £20 on my heating bills every year. So £20 on my heating bills I'm saving every year. It cost me £80 to install. Then the payback time would be, quite simply, 80 divided by 20. 80 divided by 20 is 4, and it's going to be 4 years. Okay. So what does that 4 years mean? It means that if I install loft insulation, if it cost £80 and I save 20 per year, it would take me 4 years to pay back the cost that I initially put out. In other words, it's the time it takes for the savings that you make to match the cost of the product. Okay, and different methods of insulating your home will have different payback times, and you can argue in some cases that a shorter payback time is better. All right, not in all cases, but in some cases, having a shorter payback time, getting your money back quicker, is better. And this would be a very cost-effective way of doing it. Draft excluders are very cheap, and they might well save you some money on your heating bills. And because they're very cheap, the payback time is going to be very, very short. My nan used to make draft excluders, weirdly, and she used to, and some people might even know what I'm talking about, she used to actually knit these snakes. She used to knit snakes for people to put at the bottom of their doors as draft excluders. Yeah, they looked a bit like snakes, I suppose. That was nice. Anyway, cavity wall insulation. Cavity wall insulation. Your walls, more than likely, unless you live in a really old house, will have 2 layers of bricks. And in between those 2 layers of bricks, then you'll have air, all right? And just like with double glazing, that trapped layer of air is not going to conduct heat very effectively, which is good because it can prevent thermal energy transfer. And because it's a trapped layer of air, it's not going to convect heat very effectively. So it will reduce thermal energy loss by conduction and convection. And in addition to that, what some people will do is they'll inject foam through the bricks and fill up the cavity in between your 2 skins of walls, and in doing so trap that air that's there in the foam and prevent air from circulating and reduce convection even more effectively. And then finally, I just thought I'd show you this. These are shiny foam boards, so if you were insulating a room, you might use a shiny foam board. Now, why shiny? Well, the shiny is going to reduce infrared radiation. Okay, so it's going to reduce the heat lost by infrared. It's foam, so it's got lots of trapped air. The trapped air is going to reduce heat loss by convection. And finally, it's made from a non-metal like foam, and as we discussed earlier on, non-metals aren't good conductors of heat. They do conduct heat a little bit, but those air pockets inside foam are going to reduce the rate of conduction. And I think, in terms of a tutorial, that will do. Just to recap what we've covered here, the reason why thermal energy is transferred, well, it happens wherever there's a temperature difference between materials. And heat will always transfer from hot regions to cold regions until both of those regions equal out in terms of temperature. We call this thermal equilibrium, but don't worry about that. So heat will travel from hot to cold. We talked about the density equation, which was important for us to understand the concept of density. Density is important for our understanding of conduction and convection. We also talked about how we can determine density for regular and irregular solids. We talked about the three states of matter briefly, and the arrangements of the particles. We talked about thermal energy transfer in solids through conduction, thinking about the motion of particles. We also discussed thermal energy, how it's transferred through metals, more and why it's transferred more effectively than in non-metals, all to do with those free electrons. We described convection, and we've got two really good answers in there for describing the process of conduction and convection. In terms of particles, they are on the slideshow, which you can refer back to. And then we talked about ways and means by which we can reduce the amount of thermal energy lost in the home, saving us on our heating bills, and maybe one day, who knows, helping to save the planet a little bit. So that's the end of the tutorial on thermal energy transfer. This was suitable for GCSE level. So thank you for listening, and good night.